Hello everyone, my name is Ruxian Cong, a student of Beihang University. I'm briefly introduce our paper. Compared to traditional language, the information in angular dimension of a field is beneficial to past tenses and can be used for many applications. Current works utilize 4D light field one-sided fields to fully explore spatial angular correlation. Both patch-based input and image-based input face challenges. Here is a figure about our work. Explore information from reference views to central view. In this paper, we propose a well-engineered framework called LFINet, which includes two methods to jointly explore left field for semantic segmentation. One is implicit feature integration that learns unified representation within central view and across views through attention mechanism. The other is explicit feature propagation that works feature from other views to central view under the guidance of disparity. This is the overview of LFINet. It contains four main steps. 1. Feature extraction. Central view and reference views are fed into a shared backbone, in which reference views are randomly sampled from one of the 8 image stacks, whose viewpoints change along horizontal, vertical, left and right diagonal direction in order. 2. Disparity estimation. Entire light field is fed into a disparity estimator to get disparity carrier used for subsequent steps. 3. Feature enhancement. This step aims to fully explore information from reference views to reinforce central view. We propose two approaches called implicit feature integration and explicit feature propagation to supplement central view. 4. Feature fusion and decoding. Finally, the enhanced features of two branches are aggregated and fed to a decoder to get the final segmentation result. Here, we describe the implicit feature integration in details. Attention mechanism is a valid means to implicit retrieve information by mapping a query and a set of key-value pairs. In spread by list, we incorporate self-attention and cross-attention for implicit feature integration to enhance representation of central view. Specifically, self-attention aims to aggregate contexts within central view, while cross-attention explores complementary information from reference views. Considering that repeat contexts among views have already involved in self-attention, cross-attention should pay more attention to inconsistent regions among them. To achieve this, the first step is to judge inconsistent regions. We find that these regions can be expressed as pixels with large disparity. To this end, we generate an attention mask for each reference view by computing disparity offset. Then, for large disparity areas, we enhance the cross-attention weight to reinforce focus on inconsistent region. Here, we describe the explicit feature propagation in detail. Disparity information reflects pixel offset among different views. The photo consistency assumption can be formulated as follows. Therefore, we explicit warp features from reference view to central view under the guidance of disparity to enhance central view in a different way. Taking into account that each reference view contributes differently to final representation, we adopt channel attention to generate this for aggregating aligned features and get the final output feature of explicit branching. To train our proposed LFINet, the total loss consists of 3 parts. The first term is the mean cross entropy loss at the end of network. The second term is an auxiliary cross entropy loss that is dedicated to optimize the feature extraction backbone. The third term is an auxiliary cross entropy loss to constrain the propagate feature in explicit branch close to the feature of central view. It also trains cascaded convolution layers, which are used to rectify the estimated disparity. In this part, we introduce comparative experiment and briefly introduce the ablation study. We adopt the only available benchmark MLF to conduct experiments. Considering that the available light field semantic segmentation approaches are rare, the comparison is also extended to other image-based, video-based, and RGBD-based methods. It can be observed that our LFINet achieves a state-of-the-art performance on both urban LF S1 and urban LF real, which indicates the proposed method effectively leverages complementary information for robust light field semantic segmentation. Here are some results for the visual comparison of different methods, best viewed with zooming in red and green. It can be observed that our method gains good segmentation results at the edges and occlusion. We also make evaluation studies to validate the effectiveness of prominent components in our method. For feature enhancement, we can find that both implicit and explicit manner exert their own advantages and gain better performance with combination framework. Once you remove one of them, there will be a performance degradation. In the proposed LFINet, feature propagation in the explicit branch is implemented based on disparity, and the implicit branch also applies disparity to enhance attention weight. For effects of the quality of estimated disparity, we can find that aggregate disparity period contributes to feature enhancement of central view. Besides, we studied the effects of the number of reference views. More reference views images helps to improve the accuracy, but the performance tends to be gradually saturated. Here we conclude our work. In this paper, we explore that field semantic segmentation from a brand new perspective in order to take full advantage of additional angular information embedded in that field. We propose two various manners: implicit feature integration based on similarity and explicit feature propagation relying on disparity to enhance features of central view image. The implicit and explicit combination framework can exert their own advantages and gain superior performance. However, there still exists some limitation. In the proposed LFINet, the disparity estimator is isolated and cannot be optimized during training stage. A corresponding subnetwork needs to be implemented for disparity estimation to make the whole framework can be trained in an end-to-end way. Thanks for your listening. More details can be found in our paper. If you have any questions, please email to me.